Welcome, first of all, from wherever you're joining, whatever time zone you're in. Here in Kingston, Ontario, it's beautiful and sunny, which is nice. We haven't been able to say that the whole summer. And we're really happy to be able to share with you some of the details behind our new HDF5 based file format for motion capture analysis. This is something that we introduced last month, just before the World Congress of Biomechanics in Vancouver. And we've had a lot of really good conversations with users, both in Vancouver at the World Congress and also last week in Loughborough at the International Society of Biomechanics and Sports Conference. And so we're excited today to get into maybe a bit more of a deeper dive than we can manage at a conference, and to share with you some of the details that went into our thinking about why we created this file format, what kind of problems are we trying to solve, and then some of the technical nitty-gritty that will help you take advantage of the new features that are available and understand where we're going with this new file format. So a couple of things to talk about here. First, as I've been mentioning, we see that biomechanics is moving beyond the lab, and this is a really good thing. We're able to capture outdoors, we're able to capture in competition, we're able to capture activities of daily living. We're starting to see longitudinal studies because motion capture is becoming more feasible. And all of these things are giving us as a field a lot of really good opportunities. And so we've introduced this new analysis file format built on the HDF5 format, which itself is open source, to replace our legacy CMZ file and open the door to all of these exciting opportunities for the field of motion capture. And really, our vision is for this to become and to be an easily accessible file format that stores motion capture measurements, analysis, and context all in one place. And so that we can have a biomechanics community that easily shares data with collaborators, with reviewers, with athletes, with patients, and helps us to expand this research beyond single labs and helps motion capture have the impact that I think we all believe that it can have. So last slide from me. Today, you're going to be hearing about our motivations for the new file format, really why we built it, from our CEO, Scott Selby, who I'll be handing over to in just a minute. And then you'll get a technical walkthrough of the file format, what that gives you, what that delivers, from Amr and Clark, two of the software developers here at HasMotion who are integral in developing and implementing this feature in Visual 3D. And we'll wrap up with a Q&A. So we'll take any questions that you have, and we as a team will do our best to answer. From this, we will be accepting questions through the chat, or I think we'll be able to have people ask questions kind of live if that's your preference as well. And that'll kind of take us to the end of our time. So without further ado, I'll turn it over to Scott Selby.
Okay. I'd like to thank everyone for attending. I'm starting with an old slide. It may not be a slide that I'll present very often anymore. This is from the American Society of Biomechanics last year, and this was a big surprise to me. It was kind of a made-up debate. And the question was not, are we ready, or do we have big data? Because even last year at this time, data was everywhere. The proliferation is astounding. But are we ready for it? And so Kat and Janie did their best to convince everybody for and against the idea. And much to my surprise, the majority of the audience thought that biomechanics as a field wasn't ready for big data. Considering that it's already here, this is a surprise to me. So there are regulatory aspects to that, and that's not what we're discussing here. We're discussing here how do you save data? So part of the issue is we don't really have a good mechanism for sharing data. What file format? What should be in that file? So essentially, in a very crude schematic here, people are collecting lots of data. And of the many applications, a lot of the data is pumped through some neural network, some large language model. And you're trying to find a collection of people. You're trying to identify a disorder, whatever. The idea is that you just ingest a bunch of data, however you've got it. You throw it at a neural network, and the neural network will pick out the wheat from the chaff, and then you'll have results, and you'll be able to act on them. Well, it's not quite that simple. There's many, many steps between this pile of data that's accumulating and actually trying to analyze it in some structured way. The terms down here are really computing terms, but the gathering data, that's really what our core product Visual 3D has been doing forever. People have recorded movement and processed it, they've modeled it, they've mapped from whatever recordings there were to something about human movement. And then the fun begins because you have to clean it. Data's never perfect. And cleaning does not mean throwing away data you don't like. It just means throwing away data that you know doesn't reflect what was recorded. It could be as simple as you missed the force platform, so you can't do inverse dynamics. So you don't want to include that trial. Shaping data forever in our field has simply been time normalization. There are much more clever ways of normalizing signals so that they can be combined. But the big issue here is how do you save this? That line in the middle, the green down arrow really should reflect how's this data stored? Well, here's our proprietary format. It's 2001. We first introduced it as what we called then the CMO format. It's proprietary, but it contained the entire workspace from our software. It contained all of the original or raw data that came in. It contained all of the process data, all of the things that Visual 3D did to that data, logged, so that if you looked at any of the derived signals from your raw signals, you knew where it came from. It included all of the mapping, all of the calibration. It included the reports. It was a file format that still is very functional, but not practical for two fundamental reasons. The elephant is it's proprietary. And we can't go about having a public, collection of data that's only based on proprietary data formats. And secondly, it wasn't really meant for 100,000 subjects. So where are we going? It's not as if we were first at this, and it's not as if we were the first to even decide to use HDF. HDF has been around since 1986. There is a not-for-profit organization that supports this file format, that they will help you as they helped us. So it's a bit scary to go to a file format this big. If you look at it on the website, you will see page after page, and you'll see a lot of terminology that people like me don't know all of it. And so for me, it was a bit magical, and so been a bit reluctant to step into this, despite all of the groups. And I'll point out MoveX for one, that really says this should be used in biomechanics. It's used everywhere. I'll let the programmers explain how we interact with it. But if we're going to release this, if we're going to, as a community, decide how we're going to save data, I'm not sure it's that helpful to ask people what they think and only give them what ifs. we think it's important that people have their hands on it so they can say, oh, gee, that's what you meant? No, I don't like that. Or I wish I could do this. This is way beyond our file format. It doesn't contain some of the things that are nice for us about our file format, but it is accessible. It is open. It allows any kind of metadata. It allows any kind of data. And so partly what we're doing with this webinar is just staking a claim and say, let's really talk about something concrete. Let's show you our first instance of it, which is simply replicating the data from our file format so that our software can open and save it just like it was our file format. This is where we're starting, and we'll let people tell us about it. And I think now I'm going to pass on to the programmers because this isn't scary. So let's let Clark and Amra talk about it.
Hello. Yeah, can you see my screen? Yeah. Thank you very much, Scott, for this introduction. And just to give a little bit of an idea of what is an HDF5, HDF5 is an extendable data model. That means we can, or someone can take the file format and add the data to it, change the data type without actually breaking the structure of the file format. It's also open source and self-describing. Self-describing means that based on the person who wrote this file format, you can ask the file what it contains, what kind of groups, what kind of data that is actually stored inside the file format, and you can perform a read or a write into it without having to read the entire file structure or the entire file format. You have to parse the entire data that is actually stored inside this file format. So why HDF5 is chosen out of all of the open source file format is that HDF5 is actually commonly used in a lot of fields other than biomechanics. It's used in aerospace. It has been most commonly used in aerospace. It's also been used in finance, in healthcare, and also a lot of fields in deep learning. And it specializes in storing a complex data format, or especially in biomechanics, when we want to store something, we store motion files, C3D files, information, structured data, unstructured data. And for example, you might have huge signals with different data types that exist that you have to parse and read it. So storing or organizing this kind of bookkeeping for each tribe, you can, for example, have a single file or a single group for each tribe, or you can store each modality such as force data, analog data, markers separately. And for example, if I want to group all of the data that belongs to one subject, I will have to parse multiple files for each modality. But if I group my file format based on the subjects, if I want a single modality, I will have to parse all of them separately. So it will get complicated pretty fast and pretty messy because all of these different modality that we want to store in biomechanics. So HDF5 basically solves this problem by creating a tree data structure or a tree structure. This is very similar to what you have in your operating system. They had this idea from Linux. So, for example, if you open your computer, your operating system does not read every single file that's stored in your hard disk. It basically reads the tree that defines all of your files and all of your folders on your computer. This is how operating systems does its bookkeeping. It is very similar in HDF5. It stores a tree structure. It has something called groups, which is similar to your folders, and it has something called datasets, which what we use to store signals or even strings. And for each group or a data set, we also have something called attributes. These attributes are basically metadata that you pass to the person who reads this file or the program who reads this file in order to be able to interpret what is stored inside the file. And for our structure for HDF5 that we use to replicate the functionality of the CMZ, we divided the file format into 6 primary groups, and also feel free to browse into, and I think Clark will describe a little bit on how you can browse and read what is actually stored inside the file format. In our 6 primary groups, we have maybe the main group that has most of the data is called the movement files. It stores this .c3d informations that in your actual trials. And we also have another primary group called calibration files. This contains the static trials that has been used for marker-based motion capture systems. And also we have another group called global. This global group basically stores the information that is common between all of different C3D file format, and it has the same exact structure as the calibration trial and the movement files, but across all subjects. We also contain another 3 groups called the others group and registry group and report group. These groups are mostly used internally by Visual 3D to be able to replicate the same exact functionality of the CMZ file and return the state of the file or your workspace. Just when you click save, it just opens the same exact info and information that you saved inside Visual 3D. So right now we have a pre-released version in Visual 3D. It is actually supported by both the pipeline commands and also the UI access, and all the save options and functionalities actually has been replicated to the CMZ file for the HDF5. And I will let Clark maybe share a little bit more insight about how to view and to access the output of the HDF5.
Hi everyone. So how can we read or access data in a H5 format is extremely straightforward. There are multiple softwares or online tools that can help us to simply check what exists in the H5 file. But I would personally recommend using the HDF5 software, which is a visual tool developed by the HDF group just for browsing and editing the HDF files, and it's extremely easy to use. Here are some examples of how a group, a dataset, or attributes looks like within a H5 file when we're browsing through HDF5 software. On the left-hand side, we can see here we have a dataset being opened from the HDF5 software, and on the right-hand side is how the attributes look like when we're browsing it with HDF5 software. And for our signal data, when we're doing H5 export from our Visual 3D software, where for each n-dimensional signals, we stored it in a one-dimensional array using a flattened layout, meaning that the channels for each sample are stored consecutively. For example, if we have a 3D signal, it will be stored as x1, y1, z1, x2, y2, z2, and so on and so forth. And therefore, when we're trying to read the data from the data set in a H5 file, we need to know how many channels there are or how many elements the step size of this data set. And these values, you can find them easily from our attribute on each data set. So here, as you can see on the right-hand side, we have a quick example of the attributes of a dataset, and you can search for these two attributes named num elements and step size for corresponding values. And as mentioned earlier, H5 file format is developed and maintained by the HDF group, which is a nonprofit organization that supports HDF5 technologies. There are several resources that we would recommend checking. And if you're further interested in this group or this file format, I believe Richard can send these links in the chat. Okay, and finally, we have a quick example of how we can extract signals and data from our H5 export that was made by our Visual 3D. Well, first of all, the easiest way of checking or extracting a signal is definitely just using our Visual 3D pre-release. Is extremely straightforward, and we'll also be supporting this HDF import and export in Swift shortly. And the reason why I said extracting signals and data from a H5 format is extremely straightforward is most programming language actually support HDF5, and there are multiple libraries available for each of these programming language. So common languages like C++, and Python, they all support multiple libraries. And personally, I would highly recommend using Python as it is extremely straightforward. And here we actually have a quick example of how we can extract and plot a signal from a H5 format using Python. Once we have import the Python library, we can just import any H5 file just with the same procedure of how you can open any other file format in Python. And accessing a group or a data set is exactly the same as how you can access a value within a hash map. However, instead of using keys, we just use the path to the group or to the data set as the key. And when we're trying to access an attribute, we just use the name of the attribute as the key to access the attribute, which is also the same as how we can access an element in a hash map. And in this example, where we're trying to plot a data set with three-dimensional that has a three-dimensional signal. Therefore, we need to know how many elements exist in this data set. We can simply get that value from the attribute. As we can see here, we extract that value from num elements of that data set. And after that, we can plot the signals pretty straightforward using Python libraries. Some of the work that we're currently working on is we're trying to reduce the file size of our H5 export that was made by Visual 3D. We're also trying to improve our accessing speed when we're reading and saving H5 format with Visual 3D. And that's it. We're currently working on this, and we would really appreciate any feedbacks or suggestions that can help us to guide our future development. And we're also open to any questions. Thank you.
Great, thank you a lot, Clark. So as promised at the beginning, and as Clark mentioned, we are now open for questions and answers. I have a first question in the chat. Feel free to throw any questions that you have into the chat, or maybe just kind of raise your hand to let us know that you'd like to ask a question. Also in the chat are a number of different links that I've been putting in. So first group are the links that Amr and Clark highlighted in their presentations in terms of resources provided by the HDF group. And I've also added in a a link as well to the documentation on our wiki site that most of you will be familiar with. And this gives you a chance to see kind of our documentation of very specifically how we have implemented HDF5 within Visual 3D and to store the motion capture analysis that we're working with as a field. So just before we go to the first question there, just to give everyone a chance to think about these things, I'll ask Clark if you can just show us the HDF5 documentation on our wiki documentation site and just kind of go through the sections, the details that we've provided there for everyone on the webinar, and then we'll move into answering the questions.
Sure. Let me just find the link real quick. Yeah, so all of these resources can be found really easily from our wiki page. We provide an HDF5 documentation just for the structures that we implemented for our Visual 3D export, and along with some explanations of why we're doing this and some guidelines of how you can access the data or the structures that we built. And here's just a quick example of one of the sections in our documentation, which is similar to what Armor just presented earlier today about how our structures how the structures are being laid out in our H5 format. And yeah, that's pretty much it. And we also have sections about how you can access signals or data sets, groups in our H5 export format.
Great. Thank you, Clark. So yes, as we've highlighted, one of our big goals here is to make this data in this file format as easily accessible as possible to all of the users. So as Clark was mentioning with his example Python script, when we're naming paths or signals or attributes to pull them out within Python or whatever your language of choice is, you can certainly use the H5 viewer to have a look and poke around and see how we've stored that. But you can also look at the documentation as hopefully a more structured, more kind of a shortcut way of learning how the data has been structured there. So going to the questions then, we've got two questions in right now. So I think the first question is from Sajeda asking, can we store external forces as well? And there's a thumbs up there. So I think that's a vote that someone else would like to hear this question answered as well. So I can say briefly, before I turn it over to the technical team, that yes, we can store forces inside the HDF5 file in the exact same way that we store forces in the CMZ file. So whether that force data exists from a force platform, for example, a force measurement system that's been already synchronized and brought together by the motion capture system you're using. Certainly we can read that in and represent it in the exact same way that we represent force data in Visual 3D today. And is also possible within Visual 3D to read in force data using commands like import analog signals or manage file merge for markerless data. And these are kind of two of the common pathways that we bring in external forces within Visual 3D. Are there any other questions? So a follow-up here. Difference between the ASCII data we export from Visual 3D and from HDF5. So it's a great follow-up question, and I think this really gets to a key point that we're trying to help users with. With HDF5, there should be no need to export to ASCII. So whatever purpose you are exporting your results to ASCII for. Usually that's because you're trying to move the data somewhere that can't read a CMZ file, or you're trying to share it with someone who doesn't have Visual 3D. One of the really nice things that we get by having implemented an HDF5 based format is that instead of having your collaborators or your other systems read from ASCII, they can read directly from the HDF5 file that you've saved. And so this avoids having duplicated copies of the data. So having both the underlying data in your CMZ and an ASCII export somewhere else. Because at that point, we start running into questions of, are the results, the exported results and your data synchronized? Have you exported since you last updated the model? And this is, again, as Amr was mentioning, one of the problems we're trying to solve. If we have multiple files that are affiliated with a specific trial, then the task of managing them becomes very difficult, and our experience is that things break down. So we can simplify an analysis process by taking out an entire export, taking out an entire intermediate file, and whatever you're doing with the ASCII data file, you will be able to do directly from HDF5, since as Amr and Clark highlighted, a number of open source programs exist, and a number of libraries and a number of different programming languages exist to give your collaborators and other partners access to your data without the export. So hopefully, Sajida, that answers your question. So
I'd like to follow up on that a bit, Richard. This is a pre-release, and when we put out a signal, we put out the entire trial. So all the frames go out. When you want to time normalize data, when you're shaping it for a further analysis, the time normalization, whatever form it takes, that's up to you right now. So we realize that this is a challenge with this initial format. I mean, our belief is that each signal should be stored once. And if you're trying to extract, I don't know, heel strike to heel strike to toe off, several different versions of a signal, that should all be done on the fly. But that means that we have to provide a way of allowing users to extract parts, traces within the signal, just the way Visual 3D and SIFT do right now. And that is something we're working on. So if you think you're going to jump in right now and have no duplication, we're not there yet. But we need to know how to provide an API that allows you to present your event sequence, or a query really, that says how you want this signal returned to your program. That's a really important thing we're working on right now. So all ideas are welcome, but beware that right now we're not quite there yet. We know how important it is. We're working on it.
Great. Thanks, Scott. Looking through questions in the chat, next one comes from Keizo. Can you show an example of how the HDF5 file works with sample data? So I'm not sure, Clark, Amr, if we have something to explore, but it looks like yes. Amr, I'll turn it over to you.
Yeah, for the H5 file, it works the same exact way as the CMZ. So, for example, here, if it also the same exact way in the pipeline, but let us show the UI first. If you open a file, open an add, you will find that here in the latest release, we have a .h5 file that has been added to the first option, and we can just open an example.h5. And it has the same exact functionality as the CMZ for now, and also the same way in file open. I can execute pipeline and yeah, maybe ignore duplicate because I already opened that. Yeah, okay. So also, and for saving, the same way you can just expand this part and choose an H5 file if you want to save your workspace an H5 file and name it example2, for example. And save. Not save. Oh. Not sure which version you had, but yeah. Example2, yeah. Any questions?
Yeah, I guess two things, Amr. Can we show just the signals and events tab here just to kind of walk through how
Yeah, yeah.
transparent this is to the user, whether we've loaded a CMZ or an HDF5 file,
Yeah.
and maybe if you have HDF view on the computer.
Yeah,
Join that.
1 second. For the HDF view, desktop samples, here it is. This can be installed from one of the links that we have as a resource, and you can freely browse what we actually stored inside HV view. We have here in the movement files. This is the movement files, and this is the data tree of the HDF5, and this is, let's open that. For example, here. For example, the data tree that you will see in signals and events tab is actually the same one, the same data tree that is stored inside the HD5 group. Let me just make one good example to that. Yeah, event labels. Yeah, this one. And Max. Yeah, I think I used.
I think that is pretty clear there, Elmer. Just to show what the file looks like both in HDF view and in Visual 3D. And again, in Visual 3D, when we're looking at an HDF5 file that we've loaded in, there's nothing different compared to what happens when we load in a CMZ file. We've stored the same information, and when we load it in, we present it to the user in identical ways. And so really, there's no change to your workflow or to how you explore the data within your workspace working with HDF5 compared with the legacy CMZ format that everyone, I think, on the call is familiar with. So unless, Amr, do you have something else you wanted to show, or we move on to the next question?
Yeah. Do I have any other questions?
Yeah, I'm seeing a few more in the chat here. So from Colin Bond, could Visual 3D call a .exe, PS1, etc., that imports the H5 file, outputs a report as part of a pipeline in the same way that we can do with SIFT's command line interface via the .bat file? So I think, Colin, your answer there is that this kind of orchestration task is something that we believe fits better in SIF's capabilities. And as you note, we can do this in the command line interface there. We're not looking to extend Visual 3D in that way. We're really focusing for Visual 3D on its core capabilities of ingesting as broad an array of 3D motion capture data as possible, representing that to the user in terms of the measurements that you've made and giving you, the transparency and the control over that data and the measurements and the analysis that you're doing so that you can see exactly the decisions that you've made, that your collaborators have made, and that you have the flexibility to define the models and the analysis items that are relevant to your research question. The kind of orchestration that you're talking about does live in SIFT, and as soon as we have SIFT released with compatibility with the HDF5 file format, this kind of orchestration would be best done there. Karen, I appreciate your comment. Yes, not all systems where you're moving the data will support HDF5, still need ASCII. That makes sense. If your systems don't support HDF5, then it makes sense that you need to have the data in a form that is supported. I think the key thing here, one is that the primary use case that users have exported signals to ASCII for is because wherever they're going doesn't read a CMZ file. And we just know that because, as we've discussed, the CMZ file format is proprietary, and there just aren't any systems out there that read it other than our own software. So with HDF5, our goal is to broaden the number of third-party systems that you can use to read and write these data file formats, but we're never going to get 100% coverage. And yes, if your third-party system doesn't work with HDF5, the ability to export data to ASCII files will be maintained. We won't be sunsetting that feature or anything like that. I think, Scott, did you have something you wanted to add?
Yeah, so it's getting other people involved. So having different manufacturers supporting the file format. The HDF group is a broad enough group that you can consult them. So that's how we got started. We didn't just leaf through the documentation. We paid a rather modest consulting fee to HDF5. And that group provided someone to guide us through and look at our files and make suggestions, and is continuing to help us. So there's a broad organization to help the manufacturers. The one thing we did in our pre-release to make it easier for everyone is we actually saved the header group or block from the C3D format as a binary block in the file, and we saved the entire parameter section as a binary block. So any manufacturer that wants to write this out could write out essentially their C3D file to an H5 file quite easily, and be read by Visual 3D and anyone else that can read a C3D file. So we did try to make it easy. Is this the long-term solution? No, but it should allow other manufacturers to adopt the format quite easily. So we are aware that one of the reasons to put it out is we need buy-in, and you can't have buy-in until there's a thing to buy into.
Great, thanks, Scott. So I'm at the bottom of the chat here. I don't see any more questions. We're at 11:45 local time here, so I think we've filled some time nicely. As always, you know that you can contact us at HasMotion, support@hasmotion.ca if you have any questions. As Clark plugged, we are certainly looking for suggestions and input from users about what types of features or what types of capabilities in this HDF5 format would be valuable to you and how you use motion capture data wherever you are in terms of your research, in terms of any of the work that you're doing with motion capture data. I'll just add at the end the sample file that Clark shared on screen. We'll share that with everyone who's been on the call here, so you have kind of a starter.py file to have a look and see how that works, and use that maybe as a model for your own work moving forward. But otherwise, thank you very much for coming out, for listening to us, and have a good rest of your day. Thanks.
Thanks, everyone.